Hello, welcome back to the educational series around electric utility transformation. Just a reminder, the series is really aimed to ensure the importance of leadership, the operational excellence, and the public engagement that must occur around the technical challenges that we're facing as we transform the electric grid to serve the needs of the future. So today is kind of diving into the weeds of a particular topic that is really hot right now, something that I brought up in the previous lectures, the phenomenon of energy storage systems or battery energy storage systems. The grid in itself was designed with the idea that there was not a piece of equipment or a capability to store energy to be used for another time at its fundamental principle. So the grid today has the ability to generate the exact amount of electron flow that is consumed by the customer. That in itself is a phenomena that I think we take for granted at great levels as a society. However, over the last couple of decades, the evolution of battery energy storage systems has been proliferating, which means that these devices are becoming scalable and usable by the masses. So there's an evolution occurring. Right, wrong, or indifferent, the devices are being adopted and evolving on the grid integration. But with that comes a large set of challenges and therefore opportunities. So this module here is to introduce some of those concepts and really the broad perspective from the moment of conception to the execution, commissioning, testing, and maintenance of said device. We won't be able to cover everything in great detail, but the key of this module is to introduce the dynamic, complex challenges that are occurring, and really the work that still needs to be done, and the information to really provide support to the utility workers that are actively and rapidly enabling these technologies to connect. And those devices are either being connected and owned by a utility and/or a third-party developer. That in itself is a complexity. So we're going to step into the challenges, the safety, kind of the standards for inverter-based resources. So I'm going to introduce a new acronym per se. The industry as a whole, as I said, we choose language, we choose terminology that is very hefty in the overall technological meat of what it means. And we tend to, as a society, throw the word around without great awareness of the weight of said term to the overall impacts of the processes and the people that will be impacted. An IBR is deemed, just as I stated, inverter-based resources, typically from the connection of a new energy source such as wind, solar, battery, and/or any device that is using direct current instead of alternating current, which the original grid currently runs on. So the transmission world and the engineers and those that are pushing a lot of the challenges that are occurring with these transformation use the term IBR. However, if you want to connect an inverter-based resource on the distribution, we as an industry have called it distributed energy resources. So just to confuse you, but it is the same complications and complicated technology that needs to connect to the grid and be integrated to the grid safely, affordably, reliably, and now sustainably and resilient. So the goal is to really help support the enhancement of the integration of these new technologies into the grid, thereby promoting and enabling dynamic customer energy transition. So in itself, having these conversations and driving the awareness is not to be seen as being obstinate or disagreeing, but bringing to the table the information so that more decisions can be made together instead of separately, creating this catch-22 of challenges that you come to understand if you yourself has tried to advance new technology on the grid. So the objective is to leverage what we know from the existing experience that we have from those that have won before and start to create the conversation and the language and the information to support and drive those that are coming. There's a huge part of just from the conception of introducing this new device to a utility that does not own or even have or operate an IBR or DER on the system. Based on the decision-making matrix, it's complex. But by adding a device to the transmission system adds complications based on the system is regulated by an organization that ensures that anything that's connected to the transmission system is within a set of very robust standards and requirements to drive security and reliability. That in itself could be a great topic of education of what that means in regards to the heightened awareness of anyone that is being asked to ensure that this happens correctly will have a whole set of requirements that they did not come up with themselves. And I'm thinking about the individual contributor within a utility being asked to take on this challenge. You have to be knowledgeable of all of the current requirements and standards that would be mandated based on this device connecting. So there's an evolution to not only the device itself and being able to contribute to this much needed gap, storing energy for a later time of use, but there's also an evolution to the management of the risk of this device might play. So to boil it down, will the device, when connected, respond when called upon? Can it be dispatchable? Can it be used in these large simulations as a robust, present source for when the grid is calling upon it? We developed an electric power grid that has the ability to have robust, large amounts of generation running 24/7, 365 with very limited appetite for that device to not be available at all times. It says in advance that it will be available. So here comes a new technology that will experience an inevitable amount of thousands, if not millions, of scenarios that we need as an organization of people to trust it will be available when called upon. And I think that's the fundamental concern that really is sitting at the bottom of all questions and concern of said new device being connected. So it's not the complex other reasons, but for the one that is in charge of ensuring the safe, reliable, affordable use of the grid, that is what they're thinking. Because they will be the one held reliable when it does not perform, even if it's not their device that they own. Just to kind of give a layering of topics, high-level language, which each word in itself has a heavy lift inside to understand who needs to be educated and understand the phenomena, and how will that be done, but then how will these various challenges be made whole. And also remembering that there is no peanut butter spread solution, but there is a synergistic, collaborative conversation that needs to happen from all parties of the industry. So, grid stability. And I spoke to that. That's probably number one, especially on the transmission grid. Our transmission grid is maintaining power 24/7, 365 under 60 hertz frequency, just for this grid in the States, which means that you have massive machines spinning at 60 hertz, 24/7, 365, and the room for error is very limited, less than 0.5% hertz. If something would go off kilter, say a major disruption or system faults, if those large systems are not able to maintain stability, you can have cascading blackouts. So if we have a large enough set of IBRs that are not coordinated to the grid to maintain that stability, there is a concern. The other challenge is grid integration in itself. And when I say that, more or less designing the integration, so not only is it just an inverter, within that inverter is a whole construct of other pieces of equipment that must come together to be able to develop the large energy source. And so just an example is the container for which it sits in, the control and protection of the batteries and all of the racks in themselves, the heating and cooling of said systems to ensure safety, and all of that then has to be integrated into the grid. The challenges of the operations, which is deep and heavy, as well as the varying technology that is showing up within the inverter space itself. On top of the inverter, you have the actual technology of your stored energy cells. The other area is interoperability. and its ability to communicate not only to itself within its self-contained system, but also to the overall communication of the grid. There's a cost element, which is a very large contributor to a lot of decision-making power. Is this cost effective? And what does that mean? And then lastly, which plays to the cost, is how can this device serve in the current energy markets that are constructed in our industry today? Another area that the current systems that are available and being deployed, and does not mean that this is always the case, is the concern around safety. So a significant portion of the work and the standing up of reskilling and bringing awareness to the phenomenon is batteries and their fire risks. So with the current chemical makeup of the batteries, they are and have been seen to catch fire, causing by either electrical faults or mechanical damage or just thermal abuse. All that to say is this is a fast and rapid improving space, but it's something that cannot be taken lightly. So there's comprehensive fire safety measures that are being done for every project that's being installed to the grid. The number one foundation to all operations of any utility is the safety, not only of the workforce, but of the public. So safety is taken into consideration. And one thing that has been experienced over this growth, which happens with driving innovation, new technologies, is scenarios that have been failures that we have learned from. So there's something called thermal runaway, which is where the increase in the temperature within a battery cell can cause this self-sustaining series of reactions that leads to a heat generation that will ignite a fire. There has been many opportunities to study this phenomena and start to develop preventive measures that include the overall design of said battery systems, the coding of the systems, and then the battery management system. So when we say battery management system, it's software that's monitoring and controlling all of the operational parameters of the battery energy storage system itself. And in this module, I'm leaning heavy on integration of IBR because the batteries as we know them today, which doesn't mean they will always be made up of a certain chemical that is today, because there's a significant amount of research that is changing as I'm speaking here today. But the ability to ensure the safety becomes a challenge that we must meet head on before we can explore and deploy at a rapid pace. So I just wanted to mention safety because it's at the forefront of the industry that's actively being investigated, designs are being properly put in place, and the studies and the analyses are happening to ensure that this is not the overall option forevermore. To do so, though, comes a large amount of requirements of development, because it's new, of new codes and standards for said IBR resources. And I just want to share very quickly that it isn't not happening, but it's a part of the industry that is active and engaged, and there's a large amount of work that still needs to be done, but there are entities that have this conversation occurring. And here is a set, just for an example, of codes and standards that are actively engaged, moving forward, already in place or being worked on. And so this is a resource to realize that when there is one change or one device, it can create a massive amount of work that is required. So here are examples of some codes and standards that have been developed as we know it, and these will ever evolve as this technology itself evolves. What we just went through from a project conception is you have someone that has the idea or drives the need. You have the ability to plan, aka the position or place of where this system will go. You have the process in place of how the system will interconnect, which in itself is large in regards to contractual terms between the developer, the utility, etc. Who is held accountable and how is this device going to perform during all of these scenarios that really cannot be predicted. But that's where the standards come in. So let's say you get to the point where you're executing and agreeing as an entity to allow said device on system. Project siting is a huge topic. The permitting environmental considerations is also a huge consideration. The design, the overall design, taking into consideration of everything I spoke of, and then being confident in the procurement or purchasing of said device. Because these devices themselves are new to the utility space, and there's something very different between utility grade and commercial grade. You cannot learn or understand that experience until you are an entity that would like to connect to a utility grid. And the reason why there's a major difference between those two prepared pieces of equipment is that set of requirements and standards that I spoke of earlier that have been created to ensure that the grid maintains stability 24/7, 365. So it's a trickle-down effect. But once you procure it, that device itself needs to be held accountable to all of those. And who are the parties that will be? And lastly, another area is decommissioning, which in itself is a whole set of processes and understanding of what happens after end of life. So you could step into each one of these from project siting as an example, land availability, all of the auxiliaries, and then also civil and structural. This is for any said project, but there's certain caveats that become a little bit more unique when we're talking about placing a large battery energy storage system in someone's backyard or in a neighborhood. The other area is permitting, which leads into the permitting and environmental impact. Again, all of these topics and new ideas trigger current processes to behave differently. So even the engagement with the utility commission, as well as your community engagement plan, as well as understanding the environmental impacts of something that is new to said group that has been in charge of said questions, have never even seen or understood what battery energy storage is now being asked, what are the impacts? That requires a reskilling and an awareness and a continuous learning approach. The third is being able to understand and quantify the demand profiles that can be then used into the overall operation. It can also, you take those demand profiles, layer into a cost-benefit analysis. So someone at some point in time has to determine how much will this cost and what is the benefit to not only the utility, but ultimately the customer who will absorb the costs for the utility to integrate with. And another big area of consideration is the battery losses. There's a phenomena where if you have a 5 megawatt battery, there are varying degrees of efficiency for how much energy it actually takes to fully charge said battery after its discharge. So just as an example, no quotes, let's say you have a 5 megawatt battery, but it takes 55 megawatts to fully charge. There's a loss there. And that in itself is an ever-evolving number based on technology development, but then ties into your demand profile as well as your cost-benefit analysis. Other considerations, especially in the procurement process, is the language and information needed for your performance of said battery, which I've mentioned, as well as the warranty, which is very critical, as well as the cost and availability of spare parts, and then lastly, the training that is required for the utility to understand what this device is now that it's connected to their grid that they're regulated and mandated to operate. All of those are added cost and language and information that we need to be aware of so we can drive fruitful conversations that come to a synergistic and appealing decision at the end. So, lastly, is kind of all of the other topics, and this is not to overwhelm, but my vision here is that you're taking notes, you see this information, and you can help advance these conversations when you find yourself in a space to do so. So there's regulatory compliance, there's also the disposal of the components, there's again that environmental impact assessment, there's all of the safety protocols. A key one, which is very difficult, is who is in charge and will drive all of the stakeholder engagement. And lastly, that we all know and love, is documentation, documentation, documentation. And so if you would summarize all of those topics, I think you can envision that this is not one person, one team, one goal. This will take multiple mindsets, multiple technical expertise, multiple leadership skills to really drive all of these entities to the conclusion of a safe, reliable, and supportive resource to the overall transformation. And again, just a reminder, this is one specific technology. So if you listen to my earlier modules, this type of change or request of new technology is happening from various perspectives. So IBR is really, it kind of contains a lot of this perspective that I spoke of, but then the back end, the actual battery, creates a whole other set of complexities, as would wind, solar, or vehicle to grid, say, charging. The purpose of this module is to introduce some of these lofty topics that the industry in itself are actively pursuing, and that we need to continue to meet as an operational excellence perspective of the technical phenomena to identify these gaps, create the action plan to eliminate those gaps, develop partnerships, and create funding resources so that this is all not on our customers and overall cost to receive power, but really the funding from many resources to advance technology. And just realizing the alignment of standards is critical to unleashing this capability. So all that being said, with the integration of new devices, aka inverter-based resources or demand energy resources, comes a full suite of expertise, topics of interest, and conversations that need to be had to move said technology forward. And that in itself is where operational excellence and the correct leadership is needed, and hence the purpose of sharing this with you today. I look forward to continue to share more additional insights gained from all of the collaborative conversations that we have here at AEIC and how we can advance a lot of our transformational change together. And with that, I will wrap it up. This is another complex topic, and there's many more to come with additional information around various new technologies that is challenging, but also provide great opportunity for the new energy future that we all look forward to.